Part 1. Acid Ionization and Strength. In this video, we will be dealing with the Bronsted-Lowry acids. So these acids donate an H plus to the solution. And the H plus, this H plus right here, is usually referred to as a proton because the H atom from which it is derived loses its electron. So you can see the H atom lost this electron. This electron is separated from the single proton that the nucleus of the H atom consists of, and only the proton is left. So when H becomes H plus by losing an electron, there is only that proton nucleus left. So H plus are usually also called protons. The general notation for a Bronsted-Lowry acid is HA. When the Bronsted-Lowry acid reacts, it usually ionizes and dissociates. That means it separates into ions. And typically, in this case, it would separate into the H plus ion, because the Bronsted-Lowry acid yields an H plus, and the A minus ion. Since the A minus is a negatively charged ion, we call it the anion from the acid. This is the basic reaction that the Bronsted-Lowry acid undergoes. However, when an acid dissolves in water, the reaction on top here is not representative of what actually happens to the acid, since in the water we have water molecules interacting with the acid. What actually happens is that when the acid dissociates into its ions, the H plus ions that came from it bind to the water molecules drawn here. And this binding action forms the hydronium ion. These H's right here bind to the H2O to give the H2O an extra H, and this forms the hydronium ion in water. Meanwhile, the anion from this acid remains floating by itself, well, at least in this case. So the acid strength depends on the concentration of the H3O plus ions in the solution. A higher concentration signifies that the acid had a greater degree of dissociation and a greater strength. In order to measure the strength of the acid dissociation in water, we have to use the equilibrium equation for the dissociation of the acid. And here is this equation. On the top, we have the products of the acid dissociation in water. So here are the products of this reaction, and they are on the top of this equation. And on the bottom, we have the reactants of the acid dissociation reaction. So here are these reactants, and we drew them at the bottom. And they're drawn as a product. And also, all of these have these brackets surrounding them. The brackets signify the concentration of the substances. So basically the brackets mean that here, whatever number we write here, will signify the molar concentration of the substance. For example, if there was a number 1 written here, that would, or let's say right here, there was a number 1 written, then we would say that there was 1 molar of A minus in this solution. This equation is used to show the concentration of the substances after the reaction is complete. And the reaction is complete when an equilibrium is established, meaning that the rates of the forward reaction and the rate of the reverse reaction are equal, and the concentrations of all of these substances remain constant at that equilibrium point. Only then can we use this equation. So this equation right here is, this formula right here is equal to Kc, the equilibrium constant. And the equilibrium constant basically measures how much this reaction went, let's say, forward at equilibrium. Let's say it measures the ratio of the product of the concentrations of the products to the product of the concentrations of the reactants. So this ratio at equilibrium, and that is Kc, the equilibrium constant. As you can see, the more of these H3O plus hydronium ions produced, the greater the Kc, because a greater amount of product means that this fraction will become greater, because the H3O plus increases in value here, and this Kc value will also go up. And well, let's say if that's the case, then if there is more of this H3O plus and then the Kc is higher, then this acid is stronger, because that means that it dissociated more to produce more of this H3O plus, raising the value of the Kc. So a higher Kc equilibrium constant means that the acid is stronger because it dissociates better. However, we do not use this equation to represent the strength for acids. This is because we can make an approximation. Since we are dissolving the acid in water, here's the acid, here's the batch of water we're dissolving it in. There is already a ton of water, there's a lot of water, and not so much acid. Therefore, although the concentration of the acid changes significantly in the reaction because there's so little of it, the concentration of the water changes very little, since an extremely tiny portion of it is used up in the reaction due to the tiny amount of acid relative to it. So let's say we dissolve a little bit of this acid, yeah? Since there is so little of the acid relative to all this water, even though we used up some of the water when this acid dissociated, this change in water is relatively tiny in comparison to the total amount of water here. Therefore, since the change in the concentration of the water is so ridiculously small relative to the total amount of the water already present, we can multiply this concentration of the water by the Kc right here. Why can we do this? Because this H2O right here doesn't really change, this concentration right here, because there's just so much water already present that it's a little bit of acid dissolved doesn't really change its concentration. It's negligible. So we assume that the H2O concentration here remains constant. So we can multiply this H2O concentration by the Kc at a certain temperature, because these Kc's vary with temperature. But let's say at a certain temperature. And from this we'll get another constant called Ka, the acid ionization constant, which shows the concentration of the ions produced from the acid dissociation relative to the concentration of the acid left. So since the concentration of the water here remains constant, we can multiply these two to also get another constant value. Since both of them are constant, we get a separate constant called the Ka, the acid dissociation constant. And this acid dissociation constant shows the concentrations of the H3O plus produced by the acid times the A minus concentration produced by the acid over the concentration of the acid that is left over after this reaction went through. So let's say some of this acid dissociated and produced H3O plus and A minus. We would have this portion on top and the HA on the bottom. And we would measure the relative amount of H3O plus times A minus over versus the HA on the bottom, which whatever concentration of that acid is left over. So this constant is easier to use when representing the equilibrium concentrations of the reactants and products of the acid dissociation reaction. In effect, when a lot of this acid dissolves, dissociates, the concentrations of the products on top are very high, because if a lot of this stuff dissociates, then we get a lot of this and a lot of this. And when we got a lot of these products, this product of the products, this multiplication of the products, increases in value. And because of that, the Ka also increases in value. And basically, when the Ka increases in value, it signifies a stronger acid, because it shows that this acid on the bottom, this acid right here, is better at producing these H3O plus and A minus ions, hence increasing this numerator on top and increasing the Ka value, which signifies a strong acid. So, and when a lot of this actually dissociates, very little of it, let's say, remains. So this denominator decreases, and this numerator increases. So the Ka really increases for a strong acid, because it dissociates so much. And let's say that if the acid dissociates very little, so most of this remains, and very little of these are actually produced, then most of the acid remains. So this value on the bottom is higher, and these values on the top are lower, because there's so little of these products actually produced. And because of that, the Ka is also lower. And if the Ka is lower, it signifies a weaker acid. So in effect, what we get from this is that the larger the Ka, the stronger the acid. It's better at dissociating. The smaller the Ka, the weaker the acid. It's worse at dissociating.